Right, thank you very much. So at Firefox, at Mozilla, we do a lot of the standard software practices that other organizations are doing. One of the things that we do is we run tests on every commit, and lots and lots and lots of tests. And in fact, there are hundreds of machine hours of tests run every time we do a check-in, which happens, of course, dozens of times a day. So there's an enormous amount of work going on. And this slide shows the results of one particular commit on just on Linux, and we actually run tests on Android and Mac and Windows as well. You can each of those green words there represents a successful test suite run, and each of those test suites will contain thousands, tens of thousands, maybe hundreds of thousands of tests in it. So you can kind of get an idea of the volume here. The orange words indicate test suites that failed. There was a test failure, but the suite completed, but there was a test failure detected. And the red words indicate that the test suite failed to complete because of a crash or some other problem. And what you can see, there are some failures here. What's interesting is that these failures weren't connected with the commit that caused this output. Every time we run these tests, there's basically intermittent failures happening. Some tests will fail, usually totally unconnected to what actually changed in the code. This is a huge problem because it means that we have people spending a lot of time, wasting time looking at why these, we don't know whether the commit really caused the problem or not. People have to dig into this stuff all the time. Even worse, these failures represent real bugs. It's just that but because they're intermittent and they occur with low frequency, it's very difficult to actually track down these bugs. If you have a test that fails once in 1,000 runs, it's very, very difficult to debug that with normal techniques. And that's not such a big problem if you only have a small number of tests, but if you're running millions of tests like us, and you have many tests that fail one in 1,000 runs, you're going to see a lot of failures on an ongoing basis. This is a real big concern. It's a problem that's not just a Mozilla problem. I know I've talked to people like the Chrome team at Google, have exactly the same problem, and they solve it the same way we do. When they see a flaky test like that, they disable it. And that means that you're losing test coverage, you're basically papering over the cracks. But it's the only way to cope at the moment. So this is basically just one place where non-determinism is really biting us in the software development process and generally making our software hard to understand and hard to debug. Now this is kind of unfortunate because computers are actually deterministic things. The really smart guys at people at Intel and other places have taken this really non-deterministic stuff of atoms and built wonderful deterministic abstractions on top of them. So they've done all this hard work, but somehow or another something's going wrong. And what's going wrong is that the software people, me basically, are introducing non-determinism into the system. All right, so we've got non-determinism coming from devices like cameras and mice. We've got information flowing over the network, which is changing all the time. And we've got things like timing also making our software non-deterministic. So what can we do about this? How can we control non-determinism to make the problems I was referring to earlier tractable? Well, one old idea is that you could record the non-determinism coming into the system. If you could really record that accurately, and then you could maybe later replay that non-deterministic input, then because your actual hardware is basically deterministic, we would then be able to get the exact execution to repeat. That's the core idea of what I'm going to be talking about today. This is called record and replay. As I said, it's an old idea. People have been working on these systems for decades. There's been a ton of research in the last 5 to 10 years and earlier. These are just a subset of the projects that have been carried out in this area. The problem is that we don't have this technology available in the hands of people actually using it. Anyone want to put their hand up if they've actually used a record and replay system to debug a real bug? Okay, so no one actually put their hand up, which is maybe was there one? Oh, was one. Great, excellent. Oh, one over there too. Okay, but it's far from mainstream. And Mozilla, we were looking for solutions to our problems, and those solutions don't exist. I could talk. There have been a couple of commercial projects. VMware probably had the best one, but they cancelled it for sort of business reasons that there weren't technology reasons. But basically, for various reasons, this technology has not really made it to mainstream. And so Mozilla, we decided to study the problem, see if we could overcome those adoption barriers and make a real thing. So we built a project called RR, and that's what I'm talking about today, or part of what I'm talking about today. We designed it to be really easy for people to use. We basically looked at what made existing tools hard or impossible to use and tried to overcome those barriers. First thing was that we wanted to make sure it was really easy for people to deploy. It has to run on stock hardware, and especially it has to run on a stock operating system. We didn't want to modify the operating system kernel. That makes life a lot more difficult for a lot of people, even though technically it's trivial. It needs to be really low overhead. Tools that are heavyweight, that are high overhead, people just don't want to use them. Even if it would actually really help them and it would pay off, people are reluctant to pick up a tool that's going to take a long time to run before they get any results. Obviously, for us, it has to work on Firefox. We're not doing academic research, right? Running on toy programs is not valuable to us. It had to run on Firefox from the get-go. And we only had a very small amount of resources to do this project. So we had to choose a design that was as simple as possible, as robust as possible, because we knew that we couldn't put a lot of people on this project. And that, I think, turned out to be a really good thing. So let's step back a bit and revisit what we looked at before. Basic idea is, again, we have a CPU, some kind of CPU executing user space code deterministically. We're going to record and replay Linux processes. So we want to record all the inputs coming into that process. In the case of a Linux process, that's basically the results of system calls and signals being sent to the process asynchronously or synchronously. There's going to be some observable effects of the program. We don't care so much about those, because what we really want to make sure is that user space execution is repeatable. That's what we want to, because that's basically, as Firefox developers, that's the part of the system that we want to debug. The key part of our design is what we're not doing, all right? There's been almost all the other work in this space has relied on intensive code instrumentation. Or maybe not intensive, but at least they've examined every piece of code that you're running and they've instrumented it somehow or another. That is hard. That's a bunch of work, and we don't want to do things that are hard or a lot of work because, as I mentioned, we have few resources. Also, it introduces overhead. It's inevitable. If you have to even look at every instruction to decide whether to instrument it, you're buying into some fairly interesting and expensive analysis, especially in the context of a project like Firefox, where we've got a lot of dynamic code generation coming from the JavaScript virtual machine. So we didn't want to do it, so we said, let's not do any code instrumentation and let's see how far we can go. Can we actually build a system that works? And that's kind of the research question for us that we wanted to address and solve. And the answer is, of course, yes, I wouldn't be standing here. But that's what we do. So the way that this works is basically RR uses modern hardware and operating system features to get the results that we want without doing code instrumentation. And this slide here summarizes the techniques that we're using. I'm not going to have time to go into all of them. I'll just highlight a couple of them. Basically, as I mentioned, we need to record system call results and signals. And for that, we use the Linux ptrace API, which is an old API that's been there for a long time. Another big source of nondeterminism is shared memory data races. That's a huge problem. We basically punt on that problem. That's probably the biggest, the hardest thing that we haven't been able to deal with. The way we deal with it is we basically run your program on a single core. You still have multiple threads, but we control the scheduling. And so there are no true data races on shared memory. The reason we do that is because truly low overhead, zero instrumentation, record and replay of data races is unsolvable, I believe, without hardware support. And so part of the goal of my talk is really to explain why what we're doing is great, but we really need the hardware support to make this great for parallel programs. For us, Firefox is not very parallel, especially when it's running our test suites. So it's actually fine for us to take this approach. Another big problem is recording and replaying the time of asynchronous events, which I'm going to talk about in a minute, and then some optimizations that we do to make the overhead really, really low. One thing I want to point out is that of these features that are listed here, many of them are relatively new. Many of the Linux kernel APIs we rely on have only appeared in the last few years. So we've actually reached, without really realizing it, we've actually reached a sweet spot where hardware and software features are now available to make all this possible. A few years ago, we couldn't have done this the way we've done it today. And that's really interesting and kind of serendipitous, because these features we're using, we're not designed to do what we want to do. We're actually kind of abusing them or repurposing them for our tasks. So that's really interesting to me. So the problem of event timing is that you have your in this case, we've got a program that says, wake me up after a certain amount of real time has elapsed. And it runs for a while, and then there is a signal sent to the program there. Now, the problem is, of course, that during replay, we need to make sure that we make exactly the same amount of progress through the program before the signal arrives. If we don't, we'll end up running the signal handler in a different state and potentially corrupting the state of the program, causing it to what we call diverge, so that the replay isn't doing what the recording did. So the key thing is to measure the amount of progress that the program made and be able to repeat that. The natural thing to want to do is to count the number of instructions executed and deliver the signal at exactly the same number of instructions executed as happened during the recording. Now, the really interesting thing is that CPUs have hardware support for counting the number of instructions executed. And so if we use this hardware performance counters, we can do this with essentially zero overhead. There's only one problem, which is that in practice, the instructions retired counters are not quite accurate enough for us. There are certain cases, for example, when a page fault occurs, that an instruction gets counted twice because it runs once as a trap, it goes into the kernel, it gets restarted. And that gets counted twice by the hardware. And any inaccuracy like that actually throws out our tool completely. It means that we might deliver the signal a little too early or a little too late, and that can be fatal to us. So we can't use that counter. Fortunately, on Intel chips at least, there is a counter we can use, which is if we count the number of retired conditional branches, that actually is exactly the number of actually retired conditional branches all the time on a certain set of chips, on modern chips, not on older chips. So that's lucky for us. Again, it's serendipitous. For performance analysis, for the tasks these performance counters were designed for, these constraints don't really matter, but we're lucky enough that they were met anyway, so we're able to do what we need to do. Right. Let's talk about one more optimization that we do, which relies on some more interesting features of the operating system. A key, it's a bit hard to see, isn't it? But so programs make a lot of system calls. Firefox makes a lot of system calls. And when we do a system call with RR, we're using this ptrace API to detect the system call. And ptrace basically says, before you start a system call, we do a trap from the program we're recording to RR, to the supervisor process. And so before the system call, we get to inspect the state of the program. Then we context switch back to the original recorded task, go into the kernel, do the read operation. At the end of the read, we come back out, we context switch again to RR, and we get a chance to record the results of that read call. And then we context switch back to the original task. What this means is we're doing 4 context switches per system call, no matter what the system call is. And these read calls, the cost of a single read call in Linux is much, much less than the cost of a context switch. So this is a massive amount of overhead for system call intensive workloads. So we need a way to get around that. So what we do, in principle, is kind of obvious, but although the details are very tricky. We load some code via a preload library into the recorded process. And this is some code that intercepts these read calls, and it prevents those ptrace traps in a way that I'll explain in a minute. And it actually does the read call in the kernel directly. At the end of the read call, the recorded process itself writes the results of the read call into a buffer that is then copied out by the RR supervisor asynchronously. So we don't actually need to do any traps. We're basically forcing the recorded program to record itself. And this is work that Nimrod actually worked on when Nimrod Patusha, many of you know, worked on this when he was in New Zealand as an intern. So this works, and it works really well. There's only one issue. How do we stop the kernel from doing these ptrace traps? The ptrace API the ancient ptrace API that existed for a long time doesn't give you a way to selectively trap, right? We basically want to trap on most system calls, but on these accelerated ones, we must not trap, otherwise we lose all our performance advantages. Sorry. Okay, something's gone wrong. But anyway, basically the solution is that Linux has, in the last few years, has grown an API called seccomp BPF. Seccomp stands for secure computing, and BPF stands for Berkeley Packet Filter. The Berkeley Packet Filter part is basically means it's a bytecode language for injecting predicates into the kernel. And seccomp BPF says we can inject predicates that run every time there's a system call. And those predicates can decide what to do. They can kill the process, they can change the state of the process, they can allow the system call to proceed without interruption, or they can trigger a ptrace trap. And so that is exactly what we need to decide which system calls to trap on and which not to. And this seccomp BPF stuff was added for sandboxing. It wasn't added for record and replay. So again, we're kind of retargeting some existing functionality, some new functionality for our own purposes. So it's a great time to be doing this work. And here's the results of RR. Basically, we're showing the overhead running RR, using RR to record the execution of some Firefox test suites, which, as we remember, was my goal from the beginning. As you can see, the overheads are really low, all right, for the recording phase at least. So we have Octane as an Octane JavaScript benchmark. It's pretty well known. It's about 70%, so 1.7x slowdown. That's actually quite high for RR normally. It's higher than R's normal overhead. The reason is mainly that's because we're running Octane on a single core, and the JavaScript engine is very carefully tuned for Octane and makes as much use of multiple cores as possible for things like off-main thread compilation. So we've kind of screwed that up a bit, but still the overhead is not too bad. But if you look at these other more realistic cases, which running like HTML tests, or running render, on the right we've got tests that are testing the rendering of SVG. The overheads are less than 1.5x. And honestly, we could do better. We could improve the overhead further. We don't work on that now because no one cares. The overhead is good enough, and no one's worried about performance anymore. So that's really all we need to do. Okay, so it's not enough to just replay a program. We also need to be able to do something while we're replaying it, and particularly we want to debug it. So we added support for that. We've hooked up a GDB interface during the replay, so you can debug a replay. Then we went further. It's pretty well known that if you have the ability to record and replay an execution, and you have the ability to clone execution states and make checkpoints, basically, then you can simulate reverse execution. You take a series of checkpoints, and then if you want to go back to any particular previous state, you revert to the earlier checkpoint, and then you execute forward again until you get to the place that you want to be. And so we can simulate reverse execution relatively efficiently. It takes about twice as long to move backwards in time as forwards, depending on exactly what the situation is. And so this is a sort of a kind of a screenshot sort of how you would interact, how you can use GDB with RR. And it's one of the things that's really neat is that we can use things like hardware watch points with RR's record and replay support. In this example, the program is saying, I want to watch the value of this rectangle width, and then they do a reverse continue. And so they're basically executing backwards in time until they see where that memory location was changed. Because basically you know the value of that variable is wrong, but you don't know how it got set. With RR and reverse execution, you can just directly do this. You can directly answer this question rather than without reverse execution. You have to use a bunch of tricks, and it's much slower. Use logging or something like that. But now we can answer this question directly. We can go straight backwards to where that variable was set and see why it was set. We have a full program state available. We can get the stack trace. We can inspect any data. Everything is available. And you can also do other things. You can reverse single step, reverse jump into functions, outer functions, do everything in reverse. And once you have these capabilities available, it really changes the way you debug. We're all learning new debugging strategies and trying to unlearn our old ones because this really changes the game. And these are the results that I really care about. The results are that Mozilla developers are actually using this tool. And I'm really glad to be able to say that. It's the first piece of research I've done where it's a tool I actually wanted to use myself, and other people are keen to use it without being prodded. And this is a conversation I had on IRC just last week, where Marcus is saying that that people in his office in Toronto are trying to use R as much as they can, and they're encouraging other people to do the same. And this is basically a success condition being met, I think, here. So one thing I want to talk about before I run out of time is that this is really only the beginning. So I think of R as a first step. All right, we need infrastructure for record and replay, and we've got it now. We've got infrastructure for some set of programs, including Firefox and a lot of other things. I should mention, if any of you guys know what Julia is, it's a scientific programming language, kind of a MATLAB wannabe replacement. They've been using RR to debug stuff. There's people using RR to debug QEMU, the system emulator. There's people using RR to debug all kinds of different things. It's an open source project, of course, because that's what we do. So it's not just a Mozilla thing. You can actually use it to debug lots of different things. But yes, even all that is just the first step. And I'm going to try to discuss a few ways in which record and replay capabilities could really change the way that we do everything. One thing I'm really interested in is speeding up dynamic analysis. Before I worked on the browser full time, I did a lot of dynamic analysis work at IBM, and I'm really interested. I think dynamic analysis is really powerful, and we're not really exploiting it the way that we could. And one of the reasons is the slowdown and the latency. If you want to run a tool like Valgrind on Firefox, it's a slowdown of several times, and that perturbs test results. It makes test time out. It makes developers frustrated because they have to wait, and no one wants to wait. That's human time, right? Human time is super valuable. Machine time is super cheap. So how do we speed up dynamic analysis? Well, if you have record and replay, then you can. You record the execution, and as you're recording it, you can spin off multiple checkpoints. You can split the execution into multiple phases. And each phase, you can then do a dynamic analysis of that particular phase. And if you structure your analysis right, and it's the right kind of problem, you can then combine the results of those phases, like each of these replayed instrumented executions, their results can be combined, hopefully used to construct the results for the whole execution quickly. So you can really cut down the apparent overhead of a really heavyweight dynamic analysis. And I think this area is ripe for exploitation in research and in actual tools. Another really thing that's very dear to my heart is the idea of omniscient debugging. Although we've made GDB, we've basically provided GDB with superpowers, which is great, but it's still GDB. And I don't think that GDB is like, or even Visual Studio or graphical equivalents to GDB, I don't think they're the ultimate interface for debugging programs. They're what we've built because we could. They're basically an interface to the functionality that the operating system provided to debuggers. But we can go much further than that. Imagine that we run the program and we keep track of everything the program does in a database. Everything. Like in this case, we have a table just containing all the memory writes performed by the program. Okay? So we've got the timestamp, we've got the address it was written to, and the value that was written. If I do that, I can then answer certain queries. Oh, that didn't show up. Okay, so I can answer certain queries. So if I could say, what was the value of a certain memory location at time 14? And I can say, oh, it's the first row there. It was 127 written at time 10. I can do that query in constant time, right? Because I've got an index, like all good databases. So if I do this right, I will never need to actually re-execute the program. All the information the programmer might want could be extracted in basically constant time from this big database that I've built. Now, of course, building this database is horrendous. And I've actually done a prototype of this several years ago, before we did RR, where we used Valgrind kind of instrumentation to build a database like this. And you can build an amazing debugging experience with this information. The problem is that building the database is prohibitively expensive if you're doing it the traditional way. But if you take the parallel dynamic analysis stuff that I talked about in the previous slide, I think we can actually crack this now. We can actually implement omniscient debugging in a way that's actually usable. So that, to me, is really exciting. That's one possible next step for exploiting record and replay more fully. One more thing is, imagine if we recorded everything. Could we have recording of all program executions on all our computers running all the time? Well, let's just suppose we could do that. What would it mean? It would mean that if you ever see a bug about anything goes wrong on your computer ever, we will have that captured, and we will be able to replay it, and we will be able to find the bug and understand it. To me, that's incredibly powerful. One of the most frustrating things as a browser developer is when people have a problem in their browser and you don't know how to reproduce it, and you can't figure out what went wrong. Now, it happens all the time, obviously, and we could do away with that. We could make that go away. That would transform software, I think. Another thing we could do is, in a similar vein, is if there's some kind of malicious attack and your computer is compromised, or anything bad happens, you can analyze it fully, right? If we do this right, we'll have a complete recording of the execution. We can understand how the system was penetrated. We can monitor exactly what the malware did. We can figure out exactly what information was stolen or deleted or whatever. As part of that, we can recover any lost data because we basically know what happened. So there's a ton of sort of, I think, world-changing stuff here. There's a thing at the bottom of that slide that says basically it's like having a black box like airplanes have black boxes. Whenever a plane crashes for any reason, right, they get the black box and they understand to try to do their best to understand exactly what happened. What I'm talking about is like that for every computer. It's a lot better though because it records everything, not just some subset of the telemetry. I think that would really be amazing. Now the question is, can we actually do that? Is it actually practical to do that? And I think it's not yet, but it could be, and it wouldn't be that hard to do. I don't think we need to develop groundbreaking new technology to make this possible. So the biggest problem we have right now is that in RR, and I think in this whole field, is that low overhead, as I mentioned earlier, low overhead recording of data races is difficult to do in software. It's impossible to do in software. We need hardware support. Fortunately, it's a solved problem. Papers have been written, research projects, even at Intel, have happened where basically people demonstrated the ability to do this. And they've come up with reasonably detailed hardware designs. It's basically a matter of market demand for these features to say, yes, we need this, it's worth putting this in silicon. And so one of my not-so-secret agendas with RR is to build a groundswell among developers to say, I want people to say, to chant, we love RR, free the silicon, give us hardware race detection. If we do that, maybe we can beat down the doors and we can make it happen. There's some other things we need to do. We need some kind of secure persistent storage. Obviously, if you want to protect against malicious attacks, you need to make sure that malicious software can't erase the recordings. Also, if you have persistent storage, you can reduce the overhead of recording quite a lot, right? Like right now, we have to record all the data flowing into that CPU box. But if we know that we're getting input from some storage where we know the storage will be available when we want to do the recording, we don't need to actually record what's coming in. We can just record a reference to some immutable blob and put that in. And that's basically free. And so we already have some hacks that optimize things that way in RR, but it depends on files not changing and making assumptions about which files change, which files don't. Much better to have a file system and a storage device that can just keep the stuff around. So when we replay, we have the information. You also probably want to do this in the hypervisor. If you want to record the whole system, the right way to do that is probably to put it in a hypervisor rather than try to do user space stuff, because you obviously want to replay the kernel as well in general. Now, for debugging tasks, recording the entire operating system is too expensive, and so so that's why we do it's much lighter weight to just record user space, and that's good for that. For whole system recording, you want to use a hypervisor. Now, of course, there's privacy issues. All right, I'm not going to. You don't want people to be able to necessarily get hold of your computer and replay and analyze every single thing that you ever did on that computer. So we want to make sure that these features, if they're built, stay under the control of users, not spying agencies. That's basically my talk. This is Mozilla research project. I just want to give it's on GitHub. I just want to give a shout out also to Rust, which is our other big research project, which many of you hopefully heard of. But yeah, I'll take questions.